Hello, good afternoon, my dear student. Today we will discuss about the properties of Laplace transform. In last class, we have calculated Laplace transform of some uh, basic function. For example, impulse function or delta function, unit step function, and sinusoidal signal including sine wave and cosine wave. Later on, we have covered the linearity property of Laplace transform. Today, we will cover the remaining parts of the properties of Laplace transform. So first, we will try to understand the differential property of Laplace transform. Differential property of Laplace transform. Suppose you know the Laplace transform of a function f of t. Say f of t is capital F of s. Suppose you know the Laplace transform of a function f of t is capital F of s. Now you calculate the Laplace transform of the derivative of f of t. You know that Laplace transform is nothing but a mathematical tool or approach which help us to map time domain signal into frequency domain signal. It helps us to map between time domain and frequency domain signal. We can convert a time domain signal to a frequency domain signal f of t. In frequency domain, it becomes f of capital S. So let us calculate the differential property. Let us prove the differential property of Laplace transform. Everyone calculate the Laplace transform transform of the derivative of a function, time domain function, obviously f of t. Now we will try to calculate Laplace transform of the derivative of a function f of t. So first, what you will do? First, you write the definition of Laplace transform. We know that to calculate Laplace transform of any function, periodic or non-periodic, first we will use the conventional formula of Laplace transform or definition of Laplace transform. The definition of Laplace transform, you know that capital F of s equal to integration of f of t dt, and the limit of integration varies in the range from 0 to infinite. So you first write the formula of Laplace transform. So we can write f of s equal to integration of the derivative of f of t. You can write the f of t, just you mention by this expression f of t into e to the power minus st dt. This is the formula of Laplace transform, where a prime is nothing but the derivative of the function f of t, and you write here the limit, the lower limit of this integration is 0 we have considered here one-sided Laplace transform or unilateral. Lower limit is 0 and upper limit is is infinite. Infinite. Okay. The lower limit of the integration is 0 and upper limit is infinite, and where you just mention it, where a prime of t is nothing but the first order derivative of our function f of our given function f of t dt, this thing. Okay, so our objective is to calculate the derivative, the Laplace transform of the derivative of a given function f of t. So first, we have considered the definition or formula of Laplace transform, one-sided. And according to the definition of Laplace transform, we can write f of s, where capital F of s is the Laplace transform of the derivative of f of t. We have considered f of s is equal to integration a prime of t e to the power minus st dt, where a prime of t is nothing but the first order derivative of the function f of t. That means a prime of t equal to d dt of f of t. Everyone knows it. Okay. Now what we will do? How do we solve this problem? We know that this problem is nothing but a, actually it appeared as a product integration of product of two function, for example a prime of t and e to the power minus st. To solve such type of problem, we know that we need to take help of integration by parts rule. We will use integration by parts, okay, to solve this problem, because this is a the integration is not, the integration actually uh, takes over uh, two product of two functions. So let me write this thing. You consider just you rearrange these things for easy, actually to make it easy, uh, for easy calculation. Let me rearrange this thing. So integration of, we have taken e to the power minus st as the first term, e to the power minus st, and derivative term as the second term. To solve this problem more easily, okay, so let us rearrange the expression in this manner. You write f of a is equal to integration 0 to infinite over 0 to infinite e to the power minus st f prime of t dt, where this is the first function and this one is second function. Okay, second term. So using, we can write using integration by parts rule. By parts, we can write integration of uv dt equal to first term u, then integration of v dt minus integration of first derivative of the first term. You just consider within the bracket, within a bracket, du dt integration of second term v dt and overall dt. Okay, so by integration by parts rule, we can write this thing: integration of u v dt equal to v u integration v dt minus integration du dt, and you consider, you write here a minus term will come here, a minus term, no, okay, it's correct, minus term is here, no problem. Okay, and second term, integration of the second term, this is the integration by parts rule actually. So here you consider u as the e to the power minus st, and v as a prime of t, a prime of t. Okay, and now you solve this one. Okay, you just replace your first term e to the power minus st as u, and second term a prime of t as v, and you solve this one and tell me the final expression of f of s, and limit is 0 to infinity for this case, and whatever for this case you choose that one, no problem. So now you solve it by using integration by parts rule, integration by parts rule. So f of s equal to, you can write, you can write, you take the first term as e to the power minus st, e to the power minus st, okay, e to the power minus st, and second term you see that this is dft dt into dt cancel out, and integration of dft is nothing but f of t, f of t. Everyone just see the solution part of this, that, and you can take the limit will be 0 to infinite for this case, you consider limit 0, 0 and infinite. Okay, you just put it, then you take minus integration of the product term, integration of product term. So you take what will be the value of du dt, so you would see e to the power minus st, you just here write, you just replace this, let us consider, let u of t equal to e to the power minus st, and v equal to f prime of t. Okay, we can write it. If you have any doubt, please let me know. So therefore we can write the derivative of du dt, we can write here the derivative of du dt, du by dt equal to, we can write minus s e to the power minus st. Okay, and integration of v dt, v dt, v dt equal to, we can write f of t, f of t. Okay, because this equal to v equal to f prime t, so d f t dt dt, so d f of t equal to, you will get f of t. So here we can write, everyone solve it yourself and let me know your answer, let me know your answer. You solve it using integration by parts rule, easy approach, not a complex thing. So therefore we can write du dt equal to, you can write minus s e to the power minus st, and integration of f dt equal to, we can write f of t, f of t, and this is nothing but the dt. So you just write it in proper form, superscript form, this e to the power minus st. Now you take the limit, this limit is 0 to infinity, 0 to infinity, we put 0 to infinite, so what you will get? F of infinite, here you will get f of infinite divided by e to the power minus infinite, okay, then you will get minus f of 0 divided by e to the power 0, okay, divided by e to the power 0, then minus and minus you will get plus is integration of e to the power minus st f of t, sorry, you can write you can write f of t e to the power minus st dt. Everyone, please look at the solution part of this problem and you try to understand. So therefore we can write this thing, and the limit for this case, for this integration, is 0 to infinite. So now you can say that this part is 0, f infinite e to the power infinite, okay, this part is 0, this is actually plus e to the power, you make it plus, so e to the power plus infinite mean infinite, this part will be 0, so you can write ultimate, you can write finally 0 minus f of 0, and this term we can write as a f of s plus s f of s. These are capital letter, you just replace this s using capital letter. So finally we can write the Fourier transform of the derivative. You just consider here a prime, this is, we can make it a clear difference between f of s and a prime of s. This is the derivative, Laplace transform of the derivative function. So therefore we can write the Laplace transform of derivative of a function f of t is equal to, you just consider the Laplace transform from Laplace transform of d f of t by dt equal to s f of s minus f of naught, okay. You just replace this small letter by its capital from capital S. So therefore the derivative Laplace transform of a derivative after puja vacation. After puja we will submit the lab report. Puja vacation. Okay, no problem. I will change the deadline of your lab report submission. Okay, I will change it, no problem. After puja vacation you can submit it. After puja vacation you can submit. I will change the deadline of your lab report submission, okay, don't worry, I will change, okay. Now, and one thing, let me tell you, I will provide you, or I will give you an assignment. I will give you an assignment. The topic from RLC circuit. I will give an assignment from those topic. Okay. After MTA, whatever we have covered after MTA, from that topic I will give you an assignment, and you must solve that assignment and submit after puja vacation. So therefore after puja vacation you have two tasks, you must submit the lab report and also your assignment, okay. Now you focus on the today's topic. Let me, you see the Laplace transform of the derivative of a function is equal to the product of s parameter, s variable, and the Laplace transform of the original function minus the initial condition of the function, the initial value of the function. Therefore, for a first order differential equation, Laplace transform is s f of s minus f naught. In this way, you can, okay, I will provide you the RL and RC circuit notes, RL and RC circuit notes. I will provide you. Okay, I will provide you, no problem. I will provide you RL, RC and RLC circuit notes, whatever we have covered after MT exam. And actually I have provided origin. I think I have provided the NPTEL notes for RLC circuit. Okay, so RL and RC circuit I will give you. Don't worry, I will give you. E- Uh, Actually, I have provided the note, class note for RLC circuit, RLC NPTEL note for RLC circuit. But RL and RC circuit, I will. Actually, I have provided you a soft. I have provided a soft copy of a book. Soft copy of a book. In that book you can see, the actually theoretical part of RL and RC circuit. Otherwise I will send you again, no problem. So now you tell me what will be the Laplace transform for second order differential equation, or third order or nth order differential equation. What will be the Laplace transform for a second order, third order, fourth order or nth order differential equation? So you see that Laplace transform of a first order is nothing but is f of s minus f naught. So you take the Laplace transform of second order differential equation, then you can see that you can see that it will be the Laplace transform of second order differential equation is s f of s minus s f naught minus f prime naught. Let me write it and you verify yourself. Okay, so let me write it. The derivative, the Laplace transform of second order differential equation, and I suggest all of you verify these properties yourself. Okay, the Laplace transform of second order differential, second order derivative, you write derivative of a function f of t. In the same approach, you can get f of suppose you write double prime, the Laplace transform of second order function, second order derivative, equal to, you can write s of original function Laplace transform min, here you write s square, you will get s square, everyone prove it yourself, minus s f naught original function value, initial value, minus a prime of naught derivative of the original function, initial value of the derivative of the function. So therefore we can write the Laplace transform of any order, nth order, fourth order, whatever, s to the power n f of s minus s to the power n minus 1 f of 0 minus the nth derivative f n of 0. In this way we can write. So you just verify yourself the Laplace transform of second order differential equation. Actually, this concept is very important, and it is needed to solve circuit theory problem, especially impulse response of a circuit, step response of a circuit, ramp response of a circuit. So we need to know the Laplace transform of the derivative of a function, first order, second order. Actually, you know that we have covered two types of circuit, first order and second order. RC, RL, you know, are first order circuit, and RLC is a second order circuit. So therefore, you try to understand the Laplace transform of first order and second order. It is sufficient to solve any problem associated with circuit network theory. Okay. Now you let me tell you the integration property of Laplace transform. So we just solve the differentiation derivative of a Laplace transform of derivative of a function. So in the same manner, you can calculate the Laplace transform of the integration of a function by using integration by parts rule. And the uh, the Laplace transform the Laplace transform of the integration Laplace transform of the integration of a function for example f of t will be equal to the suppose if integration let me write it I of s capital S equal to, you will get the Laplace transform of the original function divided by capital S, the complex variable. This f of is nothing but the Laplace transform of the integration function. Laplace transform of the integration function. So let me write it clearly. If I if I of S is equal to integration of you can solve it yourself, no problem, using integration by parts rule. So our function is f of integration of actually this integration. So you take double integration here, one for your function and another from another integration coming for Laplace transform. So let me write it within bracket, you write it within bracket. It's greater than the limit of this function of this integration 0 to infinity, but this thing is 0 to t. The t f of t this is our integration function. You consider within a bracket, then e to the power minus st dt. Okay, e to the power minus st dt, and this limit is 0 to t. Here you write another dt, but you change it in another form. You just consider, because this dt and this dt is confusing, you just replace by another notation, t prime. Okay, then we can solve, we can actually make difference between this integration and the integration for Laplace transform. Okay, so the limit of this integration is, you write here within bracket, the limit is range of limit is 0 to t, and for this case the range of limit is limit of the integration limit range of limit is 0 to infinite. Range of limit is 0 to infinite. Okay, any doubt? Okay, fine. Infinite. Okay, so therefore you can calculate the Laplace transform of integration function of a integration of a function, okay, using integration by parts rule as differential case. Okay, now we will try to understand about initial value theorem and final value theorem. These are two important theorems. Without any rigorous calculation, we can say the initial value of our function or final value of our function by observing the Laplace transform. Let me repeat this point. Without any rigorous calculation, we can say the initial value or final value of a function associated with a circuit, okay, by observing its Laplace transform. Okay, now let me tell you the concept of initial value theorem. What is initial value theorem? Initial value theorem. Initial value theorem help us to calculate the initial value of a function by observing its Laplace transform. So suppose our given function is f of t. Suppose the given function is f of t. Original function, suppose f of t is a given function. Okay, now you calculate what will be the initial value of this theorem, and you say the f of s is Laplace transform. F of s is the Laplace transform of the given function f of t. Okay, initial value theorem. Using this theorem, we can calculate the initial value of a function by observing its Laplace transform. Okay, so suppose you say f of t is a given function and its Laplace transform is capital F of s, and these two function f of t and f of s, one is in time domain, another one is frequency domain, are differentiable. That means you can take derivative of this function with respect to t for f of t and with respect to s for f of s. So therefore these two function, time domain function as well as frequency domain function, are differentiable. Now we will see what will be the initial value of the function. Okay, the theorem actually states that we can calculate. So let me write the initial value. Initial value of f of t is suppose f of 0. Initial value of our given function f of t in time domain. So f of 0 means what? F of 0 means limit f of t and t tends to 0. Limit t tends to 0. Okay, t tends to You write it. T tends to 0. You just write here. T tends to 0, limit f of t, and this equal to, you can write limit s tends to infinite, capital S, f of s. We will prove it. We will prove this thing. And here s tends to infinite. S tends to infinite. The initial value theorem tell us that the initial value of a function is equal to the product of s of f of s, where limit tends to infinite. Limit of s tends to infinite. Okay, this theorem tell us this thing. Okay, the initial value of a function f of t is equal to limit t tends to 0, f of t equal to limit s tends to infinite is f of s. Now we will prove this expression. Our next job or next task is to prove this expression, that initial value of a function must be equal to the product of s and f of s, and its limit s tends to infinite. Now everyone write the Laplace transform of derivative of the function. Just we have calculated few minutes back. You just use that concept. Okay, everyone write the different Laplace transform of the derivative of f of t. F of t. Okay, we will prove this thing. So now we can write the Laplace transform of a derivative of a function is equal to let me write it in terms of integration form, e to the integration of f prime of t e to the power minus st dt equal to, you can write is capital F of s minus f naught. Everyone can write this thing, and limit is 0 to infinite. Okay, now you tell me how do you prove this thing. Okay, the limit is f of t. Now you take limit s tends to 0 on both sides of this equation. Everyone take limit, you just write it in superscript, in script from subscript from, then you write, you taking a limit s tends to 0, capital S tends to 0 on both sides of the both sides of the above equation. Okay, taking limit s tends to 0 on both sides of the above equation. Taking limit s tends to 0 on both sides of the above equation. Then we can write, after that we can write limit s tends to 0 of this things. So just copy paste this part, copy paste it here. Everyone solve it yourself, and you take limit s tends to 0, limit capital is limit, sorry, limit capital is, and here you take limit within bracket, you take this terms, two terms. A's tends to 0, here you write capital A's tends to 0, and here you write capital A's tends to 0. Just arrow sign you use, arrow sign, no problem. Then we can write, now you tell me, you see these terms, if you take integration of this term and take limit, then what you will get? This is derivative, okay? What you will get, you tell me. 0 to infinite, limit is 0 to infinite, and this is f of s limit. So therefore you can write limit t tends to infinity f of t, okay, minus limit t tends to 0 f of t. So let me write it, it's better. So we can write limit f of t minus limit f of 0 equal to, you write this two thing differ, you make it separate, limit is f of s is f of, okay, here I have made a mistake, you make it infinite, everyone make it infinite, okay, everyone replace, you make it infinite, not 0, you make it infinite, okay. S tends to infinite, and take limit, this will be infinite, this will be infinite, this also will be infinite, everyone correct it, because you know that s should be tends to infinite. So limit, then we can write here, this term will be 0 actually. The limit s tends to infinity, not require this part, you get this will be equal to 0. The limit s tends to infinity, integration of a prime t e to the power minus s t dt equal to 0. If you take, and then you will get limit s f of s minus a limit f of 0, and here you see that, this limit s tends to infinite, and this term is independent of s, so you can cancel this limit part. S, there is no function of capital S, 0, this is a constant term, so you can write f of 0, and therefore the initial value, we can write this thing in a proper way. We can write f of 0 initial value, initial value of the function equal to limit is capital S f of capital S, and for this case limit will be tends to infinity, is tends to infinity. So everyone look at the solution part of this problem, I mean, okay. So therefore you see that the initial value of a function f of t or any function y of t, x of t, whatever, can be calculated or can be find out by using its Laplace transform. Limit s tends to infinite is f of s. Okay, so this is the initial value theorem. In here we have written that f of 0 limit t tends to 0 f of t equal to limit s tends to 0 s of f of s. So this thing can be proved by considering the Laplace transform of the derivative of the function of the given function. Okay, any doubt regarding the concept of initial value theorem? Initial value theorem. So therefore, we can calculate the initial value, and later on I will show you the final value of the response of a circuit by knowing its Laplace transform without taking the initial value of the function in time domain. Without knowing the initial value of the function in time domain, we can calculate its value by using Laplace transform. Okay, so this is an important theorem. So everyone must remember this theorem. Okay, in any competitive exam, you will face such type of problem. Calculate the initial value or final value of a second order network or first order network. Okay, so then you use this concept. Now let me tell you the final value theorem. The final value theorem. Okay, final value, you already realize that initial value theorem gives the initial value of a function in time domain by uh, calculating its Laplace transforms. The final value theorem tell us same thing. You can calculate final value of a function by knowing its Laplace transform. But in this case, you need to take the limit of s tends to 0. Instead of infinite, you take limit s tends to 0. Final value theorem. Final value theorem of Laplace transform. Of Laplace transform. Okay. If a function f of t, then its final value will be for a function function say f of t for a function Laplace transform of the function of f of t, you just write f of t is integration of that thing. You just consider this thing. You copy paste from the previous slide is this f of t not prime is this one, f of t e to the power minus st dt. Okay, so this theorem tell us that we can calculate final value f of infinite. Final value means f of infinite. Everyone try to understand the solution part of this problem. F of t equal to limit f of t tends to infinite. It will be equal to limit capital S f of s tends to 0. Now you prove it yourself. Here t tends to infinite, t tends to infinite, but in frequency domain, h tends to that time h tends to 0. Capital H tends to 0. So now you prove it. This is the final value of the given function. Final value of f of t. F of t is given by f of infinite equal to limit t tends to infinite f of t equal to limit s tends to 0 is f of s. Anyone can prove it because we have already proved the initial value theorem. To prove initial value theorem, we have considered the derivative of the function at first, and then we have taken the limits of s tends to infinite. We have taken limit of s tends to infinite on both sides of the equation. Okay, on both sides of the equation. In the same approach, first you write the derivative of the function, the derivative of the Laplace transform of the derivative of the function. First, everyone write the Laplace transform of the derivative of the function. After that, you take limit of complex variable capital A tends to 0 on both sides of that Laplace transform, and then you simplify it. So finally you will get f of infinite equal to limit s tends to 0, limit s tends to 0 is f of s. Limit you will get f of infinite equal to limit s tends to 0 is f of s. If anyone has any difficulty or problem to prove this statement, write your confusion in the chat box. If anyone has any difficulty to prove this expression, if infinite or final value of f of t equal to limit s tends to 0 is f of s, you tell me. So first you write the Laplace transform of the derivative of the function. We have already written that things. Let me copy that part, this thing. Laplace transform of the derivative of the function. Okay, this one. This is the derivative of the function a prime of t first order e to the power minus st equal to s f. We have already proved this part. Okay, s f of s. Now you take limit. Now you take limit of s tends to 0 on both sides of the equation. Let me copy this thing from previous slide. You, instead of infinite, you take 0. Okay, taking limit s tends to 0 on both sides of the above equation. Then what you will get? What you will get? You tell me. If you take limit, for this case s tends to 0 a prime of t to the power minus st, for this case you will get ultimate limit t tends to infinity f of t minus limit t tends to 0 f of t equal to limit s tends to 0 s f of s minus f0. So let me write this thing, no problem. We can write this limit, it's better to write it, control C. Everyone solve it yourself. Now you change this infinite 0. You change it to 0. Okay. So this part you will get, for this part you will get this limit how much? 0 to infinite. This limit is 0 to infinite for this integration. So you will get ultimate limit t tends to infinite f of t minus limit t tends to 0 f of t and limit it. Therefore 0 0 cancel out on both sides. So you just write this thing here. You write here. Everyone write limit f of t minus limit f of t, and here you write t tends to 0 and here you write t tends to infinity. For this case limit tends to infinite, for this case limit tends to 0. Now you can write limit is f of is tends to 0 minus f of 0, because 0 is a constant sum, there is no variable. So now let me write here t tends to small t, don't write capital T, you just replace it. T tends to infinite, t tends to infinite. Here t tends to 0, for this limit t tends to 0, and for this limit capital S tends to 0. Okay, so this will give you 0. The ultimate you will get this thing. Let me copy this term, Control C. You can write this thing. This will be nothing but you just replace this thing. This will be 0 0. Therefore this 0 and this that 0 will be cancelled out. So finally you will get uh, limit f of t, or just you write f of infinite, the final value of the given function as t tends to infinite, f of infinite equal to limit, only these terms, limit s f of s tends to 0, s tends to capital S tends to 0. Okay, I hope everyone understand these things. Okay, these are two important theorem, initial value theorem and final value theorem. Okay, and you note that to prove this theorem we must know the Laplace transform of the derivative of the given function. The Laplace transform of the derivative of the given function. To prove the initial value theorem and final value theorem of Laplace transform, we need to know the Laplace transform of the derivative of the given function. Without knowing the Laplace transform of the derivative of a function, we can't prove this thing. So that's why first you try to understand the Laplace transform of the derivative of the function, and then you prove these two theorem yourself. Okay, these two theorems yourself. Okay, if you have any doubt or confusion regarding these two statements, regarding these two theorems, and also the properties of derivative, integration, or others, linearity property, you can ask me. So there are so many properties. Uh, there are so many properties for Laplace transform. Uh, Instead of this, whatever we have discussed in this in today's class and previous classes, there are other properties. For example, convolution property, then multiplication property. Okay, but in this course these properties are required. Okay, the convolution property you must cover in your next semester. Okay, and it is, and convolution property is little bit complex, so that's why I skip that property. Okay, for this syllabus. So if you have any confusion or doubt regarding the properties of Laplace transform, what is Laplace transform, mathematical form of Laplace transform, singularity function, or inverse Laplace, we will discuss in next class about inverse Laplace transform and its application for network theory. In next class, we will calculate the response, unit step response, impulse response, and ramp response for RL circuit, RC circuit, and RLC circuit. Okay, RLC circuit. So I hope everyone understand the concept of Laplace transform and its importance. What is complex frequency? Okay, what is complex frequency? The concept of complex frequency. Okay, because you know that frequency is a real function, linear frequency. If I ask you the domestic line AC means, I mean, 230 volt 50 hertz. Okay, that means the frequency of the domestic line power line signal is 50 hertz. This is a real term, real number. But if you consider S domain, if you take in Laplace transform of a sinusoidal function, and you have realized or you have noticed that S is a complex term that has two parts, sigma plus j omega. Sigma is the damping part and omega is the angular frequency. So therefore S is a complex frequency. S is a complex frequency or complex variable. So therefore you can make a distinction between real frequency and complex frequency. Okay, so complex frequency concept comes in Laplace transform, or it's associated with Laplace transform and jet transform, which you will cover in next semester, jet transform. But complex frequency, this term is associated with Laplace transform. Okay, so if anyone has any doubt or if you have any confusion, you can ask me or you write in your chat box. Thank you everyone. We will discuss the application part of Laplace transform in next class. Thank you everyone. Okay, and Harsraj, you have asked that, sir, what is the number of MT exam? I already told you in, I think, previous class or before that, that everyone got a good marks, everyone scored good marks in MT exam. Okay, I can't tell you the exact number at this time. Okay, but I can assure you that everyone got or scored good marks in MTA exam on an average 18 marks, I think 18 marks. Okay, so don't worry, you just uh, try to understand the network theory concept, because in GATE exam or any other exam, competitive exam, you will get many problems from network theory related to theorems or KCL KVL laws, and also transient analysis or steady state analysis of the circuit So therefore I suggest all of you read the theory part of this subject and solve many problems, and if you face any difficulty to solve those problems, you can send me mail or you can ask me in theory class. Okay, so I will take another one class, I mean Wednesday class 20, 19, 20, 21, 21st October. That will be the last class before Puja vacation. So before Puja vacation, I will take one more class on Wednesday. So after that, you will get Puja vacation. Thank you.